Hello, today's lesson is once again about slope. I'm going to begin by talking about what I call slope sense. It's some intuition you want to develop about lines and slopes. I'm going to finish up by talking about parallel lines. Candace is going to pick up with perpendicular lines, vertical lines, and horizontal lines. And then Anne's going to end the day talking about some applications involving slope. In my part of the lesson, I am going to specifically talk about sign on slope, some intuition you want to develop about that. Magnitude of slope, some intuition you want to develop about comparing the slopes of two lines. And then I'm going to finish up by talking about parallel lines. I thought a good way to begin the discussion on sign of slope was to look at an application problem. So let's do that. The graph in Figure 1 shows the average high temperature in Portland for the first 8 months of the year. Now, before I start asking any questions about this graph, I do want to talk about it a little bit. I got on the internet and I looked up the average temperature in January, February, March, etc. in the city of Portland, Oregon. So on this graph, there's really only 8 meaningful contextual points. Those are the points associated with the numbers 0, 1, 2, 3, up through 7. The actual average temperature during the month of January, the actual average high temperature during the month of February, etc. The reason I've gone ahead and connected the dots is because one of the things we're going to focus on in this example is the trend in the data. And it's sometimes much easier to see the trend if you connect the dots, even if contextually they're not connected. So let's go ahead and ask some questions about this graph. What is the contextual significance of the point 360? Well, I'm going to begin by focusing on the 60, because that's actually the easier value to give contextual significance to. 60 is the vertical coordinate of the point. I can see on my vertical axis that the 60 is representing the average high temperature measured in degrees Fahrenheit. So the 60 must be saying that whatever month we're talking about, the average high temperature in Portland is 60 degrees Fahrenheit. How about the 3? Well, let's look at the horizontal axis. The horizontal axis is saying that the numbers are representing the number of months since January. Now, I don't know about you, but my first thought when I see the number 3, and I'm thinking months, is March. 3 goes with March. 3 usually goes with March, but not this time. Because, again, reading our axis carefully, the number on the horizontal axis is the number of months since January. When we say 3 goes with March, we're also saying 1 goes with January. But on this graph, 1 doesn't go with January, because January is not 1 month after January. January is 0 months after January. We're 1 number behind on this graph. 0 is January, 1 is February, 2 is March. That means 3 is April. This point is telling us about the average high temperature in April. So let's go ahead and write a nice, clear conclusion to the question. I'm going to give myself a little bit of room to write my conclusion. I think our conclusion might start off by indicating the point that we're evaluating. So the point 360 tells us that the average high temperature in Portland during the month of April is 60 degrees Fahrenheit. Let's ask some more questions about this graph. Does the average high temperature increase or decrease over the first 8 months of the year? Well, if you live in the northern hemisphere, the answer to this question is probably pretty intuitive. During the first 8 months of the year, the average high temperature tends to increase. If we look at this graph, there's no doubt about it. The average high temperature in Portland increases during the first 8 months of the year. It starts out at 47, gets up to about 50. It continues increasing up to about 80 degrees by the time we get to August. Notice when I looked at this graph, it was rather instinctive for me to look at it from left to right. Part of the reason that is because my horizontal axis is being measured in time. And we know that if we're asked whether something that's a function of time is increasing or decreasing, we need to think about time moving forward. And moving forward on a horizontal time axis means reading left to right. When the variable on the horizontal axis is time, it seems natural to read the graph from left to right. You want it to become equally natural to read all graphs from left to right. This needs to become instinctive for you, that when you're asked questions about increasing and decreasing behavior looking at a graph, that you read the graph from left to right. Let's get back to our specific question. Does the average high temperature increase or decrease over the first 8 months of the year? Well, we know it increases, so let's go ahead and write our answer. The average high temperature in Portland increases over the first 8 months of the year. Now, recall what this lesson's all about. It's about slope. So I'm thinking we probably got a slope question coming up. By golly, we sure do. Calculate the slope of the line using the 2 points indicated on Figure 1. So I've gone ahead and indicated that we have the point 046 and the point 779. During January, the average high temperature in Portland is 46 degrees Fahrenheit, and during August, the average high temperature in Portland is 79 degrees Fahrenheit. Notice that there's units involved in these points. So when I make my slope calculation, I'm going to include the units in the calculation. So our slope, I think I'll go ahead and use our slope formula. I'll think of this as the sub 2 point, the 779 as the sub 2 point, and the 046 as the sub 1 point. So our rise is going to be 79 degrees Fahrenheit minus 46 degrees Fahrenheit. And our run is going to be 7 months minus 0 months. So in the numerator there, let's see, 79 minus 46 is 33. So in the numerator, we're left with 33 degrees Fahrenheit. In the denominator, we're left with 7 months. Now, I think in the context of this problem, I think the number's going to make a little more sense if we go ahead and change it to a decimal equivalent. So I'm going to get out my calculator. And I'm going to ask the calculator, what is 33 divided by 7? Of course, I need to do a little action while asking the question. So there's 33 divided by 7, and I get this big, long run-on decimal. I don't really think we need all these decimals to get a sense, all these decimal digits, to get a sense of the meaning of this slope. So I'm just going to round this down to 4.7. So the numerical part of this slope, there's Mr. Squiggly equal sign, because I'm not going to state the exact value, is 4.7, and the unit on this slope is degrees Fahrenheit per month. I bet you know what question's going to come up next. What is the contextual significance of the slope of 4.7 degrees Fahrenheit per month? Well, remember, you can almost always think of slope as a rate of change. And in this example, the rate of change we've just evaluated is the rate of change in temperature over time. So specifically, what we could say is that the slope 4.7 degrees Fahrenheit per month tells us that the temperature in this case, we're talking about the average high temperature in Portland. The slope tells us that it increases at a rate of 4.7 degrees Fahrenheit per month. Now, this rate's only good from January through August, but the slope doesn't really tell us that restriction on the slope value. Alrighty, let's leave our applied example and get down to the facts that we need to have become instinctive to us. The first fact is that lines with positive slope rise from left to right. We call these increasing lines. In our last example, the temperature was increasing, the slope was positive, and the temperature graph rose from left to right. This association between increasing lines and positive slope is actually pretty intuitive. Suppose we do have a positive slope. When we read the graph from left to right, the value of the independent variable is increasing. So we have forced the situation where the run is positive. If our rise over run is coming out positive, we must also have a positive rise. When the slope is positive from left to right, the line increases. Similarly, lines with negative slope drop from left to right. We call these decreasing lines. Again, this is fairly intuitive. If we have a negative slope and we read the graph from left to right, we are forcing ourselves into a positive run. Since slope is rise over run, the only way that we're going to end up with a negative slope is if we have a negative rise. Consequently, lines with negative slope drop from left to right. Lines with a slope of 0 are level from left to right. We call these horizontal lines. If the line is horizontal, when you move from one point to the next along the line, the rise is 0. 0 divided by any non-zero run is 0. Lines with a slope of 0 are level from left to right. Let's put these facts into action. Let's look at Figure 2. Figure 2 shows 4 points. Scales have deliberately been omitted from the graph. You're going to see several examples today where the scale is deliberately omitted from the graph. What this lesson is mostly about is developing an intuition about signs on slopes and comparisons of slopes. And I'm omitting scales because if we have scales, we might become dependent upon actually calculating the slope value and miss the comparisons and intuition that we want to develop. So let's go ahead and answer this question without a scale. Let's begin by connecting the points A and B with a line. When I connect these points with a line, or in my case, a line segment, and I look at the resultant line from left to right, I see that the line is decreasing. Decreasing lines have a negative slope. How about when we connect A to C? Well, I'm picking up my ruler, and I'm connecting A to C, and I want you to notice that I drew something from right to left. That's okay. There's nothing wrong with connecting the dots from right to left. But when you're asked what is the sign on the slope, you have to take a deep breath, forget about how you connected the dots, and remember that you have to read the graph from left to right. And when I look at this line connecting A and C from left to right, the line is increasing. And consequently, the line has positive slope. And unfortunately, my universal ruler erased the negative slope that I have from A to B. But it's back now. How about when we connect A and D? When we connect A and D, let's connect the dots. Let's take our deep breath and remember to read the graph from left to right. From left to right, the line decreases. The line connecting A and D has a negative slope. How about if I connect B and C? Well, when I connect B and C, I get what looks to be a horizontal line. Horizontal lines have a slope of 0. 0 isn't really a sign, but I think the most meaningful thing I could write in my table to answer this question, nevertheless, is that the slope is 0. So it has no sign. How about if I connect B to D? Well, we're doing this thing again where I actually drew the line from right to left. But when I consider the sign on the slope, I have to look at the line from left to right. And from left to right, this line increases. This line has a positive slope. How about when I connect C and D? From left to right, the line decreases. So the line has a negative slope. Now let's change our focus a little bit. Now let's talk about magnitude of slope, which is just another way of saying absolute value of slope. In this picture, I have a horizontal line, and I've indicated that the point 3, 3 is one of the points on the horizontal line. I'm going to add a little run segment to this point. I'm going to run 2 units to the right. Notice that when I made my 2-unit run to the right, there was a rise of 0. Consequently, the slope of this line is rise over run, which is 0 over 2, which is 0. Now let's affect a non-zero rise associated with this run. Let's rise 1 unit from this point. And let's at the same time, on a different line, rise -1 unit from this point. When we do that, notice that we no longer have horizontal lines. We have 1 increasing line and 1 decreasing line. Something that I'd like you to observe is that the amount of increase and decrease is the same on these 2 lines. Consequently, the steepness of the 2 lines are the same, albeit in 2 different directions. Let's increase the positive rise even more. Let's increase it to 5. Let's increase the magnitude of the negative rise at the same time to 5. Let's see what happens to our lines. They became even more vertical. That makes sense. Since we had the same run, increasing the magnitude of the rise increased the steepness of the line. The slopes of these 2 lines are 5/2 and -5/2. The 2 lines have equal steepness because the magnitude of the 2 rises were equal when we effected an equal run on the 2 lines. So let's look at the big picture. The 2 lines with positive slope are increasing. The 2 lines with negative slope are decreasing. The line with a slope of 0 is horizontal. The lines that have the largest absolute value, that's the 2 blue lines, they're the steepest lines. The line with the slope of 0, that's the least steep line. and the lines with slopes whose absolute value are 1/2 are in between in steepness. Let's sum all this up. When comparing the steepness of two non-vertical lines, the line that is closer to horizontal is the line whose slope is closer to 0. Now there's a whole lot of words there. A couple of the words are somewhat of a technicality, the non-vertical part, so I'm going to temporarily blot those out and reread the sentence. When comparing the steepness of two lines, the line that is closer to horizontal is the line whose slope is closer to 0. This is one of the types of slope sense that you want to become sort of intuitive. One of the things that you might do to make it a little easier to remember is to replace the phrase closer to horizontal with a word or phrase that maybe feels a little more comfortable for you. For example, some people like to say less steep. The line that is less steep is the line whose slope is closer to 0. Some people like to use the word shallower. The line that is shallower is the line whose slope is closer to 0. Use whatever word makes you feel comfortable. Let's talk about the flip side of this statement. When comparing the steepness of two non-vertical lines, the line that is closer to vertical is the line whose slope has greater absolute value. Again, the non-vertical part is somewhat a technicality, so you might abbreviate this. When comparing the steepness of two lines, the line that is closer to vertical is the line whose slope has greater absolute value. There's a really common word some people choose to replace the phrase closer to vertical with. That is the word steeper. When comparing the steepness of two lines, the line that is steeper is the line whose slope has greater absolute value. Do whatever it takes to make you feel comfortable and intuitive about these two facts. Two non-vertical lines are equally steep if and only if their slopes have equal absolute value. Now, what if the two slopes not only had equal absolute value, but also had equal sign? Like, what if the two slopes were both positive? What is a consequence of having two lines that have the same exact slope? Well, they have the same exact steepness. What do two lines that have the same steepness look like? They look like they're parallel. Two non-vertical lines are parallel if and only if their slopes are equal. Again, the non-vertical is somewhat of a technicality, so you want to at least get it down that two lines are equally steep if and only if their slopes have equal absolute value, and two lines are parallel if and only if their slopes are equal, and hopefully keep it in your back of your mind that vertical lines are an exception to these two rules. All right, let's do some comparisons of slopes. Once again, I'm leaving off a scale because I want you to get an intuition about which line is steeper, which line has the positive slope, which line has the negative slope, without actually calculating the slopes. So in our first question, it says one of the lines in figure 3 has a slope of 2, while the other has a slope of 1/2. Label each line with its slope. This is a question about steepness. Both of the lines are increasing, so the line that has a slope of 2, which is a larger absolute value than the absolute value of 1/2, has got to be the steeper of the two lines. The green line is clearly the steeper of the two lines. So the green line has the slope of 2, and the brown line has the slope of 1/2. I do want to tell you that without a scale and without the problem statement, there is absolutely no way we could even remotely estimate what these actual slopes are. But we would know, nonetheless, that the absolute value of the slope of the green line is greater than the absolute value of the slope of the brown line because the green line is the steeper of the two lines. One last question like this. One of the lines in figure 5 has a slope of -2, while the other has a slope of -3. Label each line with its slope. Both of these lines are decreasing, reflected in the fact that they have negative slopes. So we're back to a question about magnitude of slope. Which of the two lines is steeper? Sometimes it can be a little tricky to figure out which of the two lines are steeper, especially when the two lines are so close, and especially when the two lines are decreasing. So let me share a little tip that I use when I'm trying to decide which is the steeper of the two lines. First thing I do is I look at where the two lines intersect. Hopefully there is a point of intersection. And then I effect a positive run from that point. So I'm going to go to the right from that point. And then I just ask myself, okay, when I rise, which line do I get to first? That's the shallower line. Which line do I get to second? That's the steeper line. Well, when I go in the rise direction, I hit the green line first, and I hit the brown line second. So the brown line must be the steeper of the two lines. To be a little less abstract about this, if this run were 1, since our slopes are -2 and -3, the -2 rise is the shorter of the two rises, and the -3 rise is the longer of the two rises. Any way you look at it, the brown line has the slope of -3, and the green line has the slope of -2. Now let's talk about lines with equal steepness, lines with equal slope. They're called parallel lines. The slope of the line in Figure 7 is 2/3. Notice that we have a scale of 1, and in my slope triangle, I have a rise of 2 and a run of 3. So the slope is 2/3. Let's illustrate that any line with a slope of 2/3 is parallel to this line. And this is a really kind of simple illustration. All I'm going to do is I'm going to take this line along with its slope triangle, and I'm going to duplicate it and move it around. And sure enough, it wouldn't matter where I moved it, I would have a line parallel to our original line. Okay, let's work an example with parallel lines. In Figure 8, let's graph the line through the points A and B. Graphing a line, need my ruler. So connecting A and B, I get a line that looks like this. That sure was an easy problem. I wonder if there's more. Yep, there's more. Let's graph the line through the point C that is parallel to the line through A and B. Well, what do we know about parallel lines? They have equal slope. So I guess the first order of business is calculating the slope of the line through A and B. I think I'm going to go ahead and draw a slope triangle from A to B. So there's my run. And there's my rise. On my run, x increased from -4 to +4, so that's a run of 8. On my rise, y decreased from 4 to -2. So that's a rise of -6. So our slope, which is rise over run, is -6 over 8, which reduces to -3/4. So what we need to do is, starting at the point C, we need to find some points that connect to C with a slope of -3/4. What's some rise over runs that simplify to -3/4? How about +3 over -4? So if I start at C and I rise +3 and I run -1, 2, 3, 4, I'll have a point on my line. So that's the point -6, 0. Remember what that point's called? It's called the x-intercept of the line. What's another rise over run that would simplify to -3/4? How about -3 over +4? So starting at C, let's go down 3, 1, 2, 3, and right 4. 1, 2, 3, 4. Well, that lands me in the dark green part of my figure, but I still think I can figure out that the point's right about there. Let's get out the ruler. Let's connect the dots, so to speak. And by George, we've got ourselves a parallel line through C. Here's another question. Two sides of a parallelogram are given in Figure 9. What is the fourth vertex? Well, I suspect some of you are thinking, what is a parallelogram? So let's explore that question. A parallelogram is a closed figure made up of 4 line segments with the property that each pair of opposite sides is parallel. So in the enclosed region of my screen, how many parallelograms do you see? I think the green object's a parallelogram, and so is the purple object. There's actually 2 more parallelograms, the red object and the yellow text box. Now you might be thinking, well, those are rectangles. You'd be right, but check it out. Look at the text box. The 2 vertical sides are parallel, the 2 horizontal sides are parallel. Rectangles are a special type of parallelogram. Now let's talk about a property of parallelograms. Opposite sides of a parallelogram have equal length. Let's explore that. Here I've created a parallelogram that just happens to have 2 horizontal sides, and I've added a little grid to help us analyze this property. Let's first observe that the 2 pairs of opposite sides are parallel. Obviously, the 2 horizontal sides are parallel. How can we see that the other 2 sides are also parallel? I know, let's use slope. If I start at the bottom left vertex and move to the upper left vertex, I make a rise of 1, 2, 3, 4 boxes and a run of 1, 2 boxes. So the slope here is 4 boxes over 2 boxes. How about from the bottom right vertex to the upper right vertex? Up 1, 2, 3, 4 boxes, right 1, 2 boxes. 4 boxes over 2 boxes. We have the same ratio of rise over run for the 2 sides that fall on the left and the right. Let's see that the lengths are the same. Well, comparing the horizontal sides, we can just count boxes. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That checks. How can we see that the left and right side have the same length? We might use a ruler. And I not only have a ruler, I handy-dandy have a ruler that just happens to have exactly the same length as the left side of the parallelogram. Let's scooch it over to the right side